The topic for this presentation today is ancient metallurgy, ancient Egyptian metallurgy. And I've brought some examples here from our teaching collection at the Institute of Archaeology along to highlight some of the aspects and some of the materials I'll be talking about during this presentation. Now, my apprenticeship in ancient Egyptian copper smelting really started as a child. I was a bit of a pyromaniac. Okay, so from there, going on into university, I got interested in geology as well as archaeology, and then extractive metallurgy, and more recently corrosion engineering. I teach in archaeometallurgy at the Institute of Archaeology, and also conservation. So my interests have evolved over the years. And when I started with the copper smelting experiments for my PhD, that was back in 1978. And it was, I was apprenticed to Professor Tilecote, who had moved from Newcastle to University College London to the Institute about at the same time. And working on those experiments, there was a long history that I encountered in terms of experimentation with metals. Now, I'm usually on a different speaking circuit than this. I go to conservation conferences, and archaeometallurgy, we almost have our own sort of life outside of reality, okay? And with these topics, I have presented them before, but in this presentation, I want to try and show how we integrate experiments into the work that we're doing, okay? Now, if we look at sources of material for understanding metals in antiquity, there are a number of areas of evidence. I think most important are technical studies on excavated metallurgical remains from archaeological sites. Excavated is highlighted there because, again, it's viewing these materials in context. If you look at a crucible without the other debris that goes around to it, you're missing part of the story. Also, for this lecture, I've wanted to highlight some of the illustrations, particularly from Egyptian tomb paintings, and talking about how those are used to help aid and also provide further context for some of the engineering aspects of the reconstruction experiments. And then, of course, our interpretations of the evidence we collect are really based on aspects of analogy, traditional metalworking, ethnographic analogy, scientific principles, and of course, reconstruction experiments. Sorry. So when we look at an archaeometallurgical site, or an archaeological site with metallurgical activities, there are a number of things that we should really expect, or should expect, to find at the site. Most important, the raw materials, and there are fragments of the raw materials scattered around furnaces, other sites, wherever there's metallurgical activity, there are associated debris with it. So the ores and the flux, we'll talk a little bit about flux, the slag, the metal, furnace wall fragments, crucible fragments. Recognizing these, it's all part of understanding the material for a reconstruction. And of course, the technical studies are essential. As Coles and others noted years ago in terms of evaluating experiments, the more characterization and technical studies are conducted on the material, the more parameters we have to try and strengthen our interpretation. And of course, it's always said that with the experiments we can never directly prove that that's how something happened. However, with metallurgical remains, we know so much about the chemistry, we know so much about the related parameters, the thermodynamics, the heat requirements, the heat losses, that we have really quite a sustainable, viable background for putting these observations that we make in terms of technical studies in context for our interpretations. So I like to think for metals, and many of the other sort of pyrotechnologies as well too, we're on a little firmer ground on some of the essentials. Of course, there are variations we're not going to get. We have choices, but in terms of these linked parameters, we're picking one as simple as melting temperature. That's very important. If we understand melting temperature, well, that leads into the chemistry, and that leads into these other aspects. So, with the approach, and this is taken from first-year text, Renfrew and Bond, And a number of years ago, well, I also work in Peru as well, and with excavations there at the site of Batan Grande, we developed this scheme for stepwise analysis of materials from archaeological sites. And we used this in our first year teaching at the Institute of Archaeology. So the point is to try and integrate these experiments and also analytical studies within the program of interpretation. So with the collection and saving materials from the excavation, one of the critical aspects is sample selection, knowing what to collect from the field, what to analyze, and how to interpret it. Okay? Sample selection is absolutely critical in terms of random or representative sampling. Representative sampling depends very much on the skill of the person taking the samples. Okay? So there are aspects that we can tackle different ways with different sample collections. Okay? Initial documentation, metallography, petrography, compositional analysis. From there, we come up with models. How do we assess models? Well, we can use them in terms of experimentation. We can try something, assess the outcome, reevaluate, formulate new questions, go back and resample. And we've done this a number of times for sites in Peru, and we've also done this for this important site that we're going to talk about in a few minutes here of Timna. Okay? So why should we experiment with ancient, complex, well, very complex, multi-step metallurgical processes? Well, we want to get more insight into what control was exercised. What is trial and error? That's been suggested many times, trial and error. What guides trial and error? What parameters were readily controlled by observation, empirical means? I can simplify many of these processes down to simple observations of what happens on observing melting temperature, for example, observing flame color. These are all important aspects. Okay? So essentially what we're trying to get at is what do we think they were doing based on the remains, and then what did they think they were doing? And that's, I think, even more of a challenge, assessing someone's motivation. Okay. Well, Marianne Murray's identified a number of problems with assessing models, tomb illustrations. You have to be cautious in some ways on identifying aspects that are maybe relevant for different materials activities. In terms of the depictions, there are specific traditions. There are representations of an ideal that meet strict conventions for iconography. There are illustrations from elite tombs and funerary temples. Many scenes are copied frequently. Okay. Depictions follow a logical series of steps, processing steps. This is very interesting because it's almost, at least some of the illustrations, you can interpret as a flowchart, a stepwise sequence of activities in terms of production. Okay. Some scenes also have captions, which are very good. If there'll be a name or a direction or something above a scene, that helps incredibly, of course. Okay? But there are problems of accuracy and interpretations. Again, they knew what they were doing. Do we know what they were doing based on their illustrations? So the illustrations alone, of course, are not sufficient. Let's look at just a few of them here. These are well-known depictions of metalworking in Old Kingdom examples here. And there are a number of publications that look at metalworking techniques, so showing chasing, polishing, raising, all of these aspects. In fact, one of the areas I think most interesting in archaeometallurgical research right now are tools and materials in the tomb of Tutankhamun. Okay? And assessing changes and soldering, replaced parts, repairs. It's all very interesting right now. Let's say a little bit about casting here, very quickly. Lost wax casting is one of those very common techniques. This is from a book that's been used in archaeology for years, from Artifacts by Henry Hodges. And it's showing, I think most students will recognize this as an Egyptian cat, yes, in bronze. And there are very clear aspects and steps in the production of a model like that. From our teaching collection, I've brought along some examples. right now I happen to be interested in Renaissance bronzes, so I have to maybe make a cat. That's the next step. These are some models of different examples of lost wax casting, where with direct modeling, the object, the cat in this case, can be made in wax with or without a core. These little pins that you see going into the side, those are very characteristic, again, for holding the core in place. The whole thing can be then invested and coated with a plaster of sorts. Okay. Properties are, again, very important. The wax can be burnt out. The void is then simply filled with molten metal, like this. There are characteristic features that one would look for on an archaeological site. If something's been done like this, of course, all the mold material that's broken off. This is with the mold removed. And then there are additional pieces on the object, a runner and a riser on here that will be cut off. And the object would be finished like this, with further tooling, further decoration on that as well, too. Okay, so that's all very well known. And if we look at other sources of material, well, particularly the tomb of Recmira and the watercolor paintings in the Metropolitan in New York, it's much more fun to go visit the site. Highly recommended. I had a chance in 1995 with an SCA team traveling with a mining engineer, so we were looking at tombs and also stability of some structures. So I managed to talk everyone into going to this tomb as well. It's a mortuary temple. It's well known. It's been shown in many of the presentations so far. And this is the scene I really find absolutely most interesting here, because, of course, this is metalworking. And we know what they're doing because, of course, there's an inscription here on the side, and this is describing the casting of a door. Okay? This is actually quite a large casting, as you can see. Some of the objects that are represented here, I'll just point them out. Okay? Here, they're pouring liquid metal out of a crucible. And in our teaching collection, we have a reconstructed late Bronze Age crucible like this. How do we know what they were doing? Well, we'll go through and analyze specks of corroded metal inside. We'll look at the glaze on the inside, the color of the red, the color of the slag on the side, and we can assess the chemistry and what's happening from there. From the composition, we can also tell what the melting temperature is. Okay? That's the first point here. Now I'm showing this in sort of an image like this because this is only one step. This is sort of the final step. Well, they have to break it out. But other things I want to point out here as well, too, is that within this whole scheme here, okay, here's the casting, but there's also melting. There are also supplies coming in here. And also, there's weighing. And this is very, very important because here, the items that are being shown are all related with this scene here. Okay? The men coming in here, what are they carrying? Well, here's one of these oxide-shaped ingots. We've seen several of these in other depictions. Okay? We find them. We've analyzed many. We've worked on them. We know a lot about their properties. The copper's alloyed with tin to make bronze. Okay? Look, here's the charcoal that's coming in. It actually says charcoal is what I've been told on here. And these are bags of charcoal. Okay? The bags are very important because, again, that's a discrete unit. So we've got weights of copper, tin, charcoal. Over here, this is important because we've got the crucible. Here's the crucible being taken out of the furnace here. The flames, okay, coming off. And of course, for this period, in the late Bronze Age, what type of bellows are they using? They're using very characteristic pot bellows. And again, this is a very important aspect of the development of what's happening here in this scene. Okay, let's go back here. Okay, so an activity like this is closely monitored. What do we think they were doing? Well, they tell us they're making a door. What they're doing here, what does he think he's doing? Well, he's keeping account of what's actually happening in terms of materials that are needed to keep these men working, to achieve the production of a bronze door. Okay? Very carefully checking what weight of copper, what weight of tin, what weight of charcoal, how many bags of charcoal. All of this information is important. And of course, it's so important for metals, it's right under the eye of Recamy-Ray here. He's responsible for all of these activities. So here we have a stepwise sequence set up showing all of these stages in the production and also the monitoring, the accounting for this. Now, if we think about that a little bit further, well, what kind of detail are recording? Well, for an analogy on here, because we've never found, at least to the best of my knowledge, a laundry list like this. Okay? So for analogy, well, let's go 1,000 years earlier. From Ebla, Tel Mardik in Syria, from a library in the tablets, there are records recording that so and so many shekels of tin to fuse with so many shekels of copper for certain objects, maybe types, for such and such a city. This is a accounting of how much copper, how much tin go to a specific task. Now, from the records, there are also names for tin and bronze, and I think we're actually to the point now of being able to identify on composition from some of the texts, some of the names that go along with objects as well, too. So it's been real interesting the way this is developing. Okay, so that's very important. All right. Now let's look at a site that's representative of Egyptian New Kingdom copper smelting. Okay? We've seen the copper coming in as oxide ingots, but there's also Egyptian production of copper. What's that like in the late Bronze Age? Well, the site of Timna, it's located in southern Israel, just across the border near Eilat. And of course, Sinai was the destination of numerous expeditions, different times, to obtain copper. The mining temple, dedicated to Hathor at the site, is dated Strata 3 and 4. It's dated New Kingdom, and this is important because it's right at the transition from late Bronze Age into early Iron Age. And we usually refer to this as late Bronze, early Iron Age, because both technologies are represented. Now with the sites, it's a mining region. It's very arid. There's no reason to be out here except for, of course, the copper. Okay? The mining areas are over here. The temple is over here. Okay? And there are other settlements in the region as well, too. With the mining region, the copper ore is really quite distinct. Okay, these are some examples of copper ore, excuse me, from Timna. It occurs as nodules like this. These nodules are harder than the sandstone. So as the sandstone erodes, these erode out. They're harder. They sit on the surface. It's very easy initially to just go through and start picking them up. Okay, and we've done this for the experiments. We've done also beneficiation experiments looking at these and the quality of the ores. Okay. If you'd like to see some of these later, we've got them up here as well, too. Now, from the archaeological site, one of the very characteristic debris that we have is metallurgical slag. Okay? Now, this is a piece of slag from a ring like this that can be reconstructed from broken fragments at the site. And this ring of slag like this weighs on the order of 30 to 40 kilograms. This is just a piece out of it. Okay? Now, if we analyze this, we get very characteristic compositions. And from those compositions, we can see what the melting temperature is. Okay, so this is really important in terms of understanding what's going on in this process. This is also very, very heavy. And based on the composition of the slag, we can see that the iron concentration is very high. So the conclusion from that, based on some mass balances, is that using copper ore like this requires another ingredient, and that would be a flux. And this is an example of some of the iron ore flux from the site as well too. And again, that's harder, it weathers out, it's readily collected on the surface. Okay? Egyptian New Kingdom deep mines, though, go really quite deep, down to, oh goodness, about 30 meters altogether in depth. So it's really quite an elaborate mining expedition in the area. Okay? So that's a little bit on the background of the technology. Here. Let's look at the furnaces that have been discovered. Okay. Here they are in plan and section. We've got slag adhering on the back wall, like this. Okay. The bottom is sort of gray and sandy. We interpret that as having the slag removed from the bottom of the furnace. Out in front of the furnace is a depression, and this is where the molten slag would be collected out in front. All right. That's sort of the model and the pieces of evidence there. Also in the back walls of the furnace are some structures like this. We refer to this as a tuyere. It's basically a hole for the airflow pipe from the bellows to blow air into the furnace, to burn the charcoal, to reach the temperatures, to melt the slag. Okay? And we've got examples like this, and like this. And here's another one from refining. Again, very characteristic. The nozzles can be in different positions. Okay? That's an important aspect of the model and the interpretation as well, too. Here's a schematic for how tile code proposed the furnaces worked. Okay. The way a furnace like this would proceed would be that the ore, the copper ore and the iron ore would be added on the top. Charcoal in the middle here would burn. Air from the bellows would be directed down through the tuyere. The whole mass here would eventually reach a temperature that the slag, remember all the ingredients are going in, that the slag reaches its melting point. That builds up in the bottom of the furnace. Reduction's taking place. A Plano convex ingot was suggested as the product from the bottom. And we've got some examples of Plano convex ingots here that we've made in some of the experiments as well. And to make it a little easier to get to the copper, the molten slag would be drained out of the furnace like this. Okay? Now, the slag is really a very important aspect of the technology for copper smelting. And on the analyses, it's this ratio of copper ore to iron ore that's so important. And also that ratio to fuel, because again, you have to get all of these materials up to the required temperatures for the reactions to take place that are desired. So, fortunately, with iron and silica, there's a low melting temperature region in here. Okay? So these are the types of compositions that were being achieved and measured for the slag for the late Bronze Age Egyptian New Kingdom copper smelting at Timno. That's some of the science and engineering. So Tilecode had done some experiments and got it up to a point where they were running through a series. They had done 11 here, he and his students at Newcastle, and then stopped. They had been unsuccessful in terms of reaching the compositions of the slag to make the experiments representative. Okay? But they were measuring all the right parameters and really developing, building up this expertise. And then in '78, when I joined the project, my role was to assess some of these points that were still unclear. Were Plano convex copper ingots produced from smelting, or is it a secondary refining product? Also, much more needed to be done with the slag and the large furnace to get the right combination. So these experiments that I started at this point were to use appropriate materials on the appropriate scale. So these are full-scale experiments that we were trying to undertake at that point. And with the accounting. This is very important because remember we have from the tomb painting, very careful, precise records being taken for the amount of copper, the amount of tin. Well, in this case, for the smelting, close records are probably being kept for the copper produced, the copper ore, the iron ore, and of course the charcoal. So these are all aspects of the background chemistry, the use of a mass balance or heat balance that we already see in the tomb of Brecmi Ray. That's sort of the level of the technology that we assume must be working here because they're producing tons and tons of slag on a very routine basis. Okay? So working from there, we had to try and deal with aspects of furnace construction, the reduction atmosphere, dealing with slagging of poor quality refractories, and this Plano convex ingot question at the bottom. Okay? So here we have one of the reconstructions that we built, full size. We experimented with 1, 2, and 3 tuyeres. We also experimented with better materials than the fire brick. We had trouble with the fire brick because we found the conductivity, thermal conductivity was too high. So we did much better with sand and clay than with the modern fire brick. Well, there are different properties. Okay? So the clay refractory was a lot of sand. We used about 10% clay with the sand for higher refractory properties. The furnace walls would stand up to even higher temperatures. But there were other aspects that with the experiments, we could see how these refractories would change. And this series of photos here, you're seeing charging ore into the furnace. This photo was done without flash, so you get an idea of the flame color on here. This is very important. Blue is good, right? That's very reducing. Too much yellow means it's too oxidizing. Okay, so we just tried to keep the flame as blue as possible here. Here's the slag coming out of the furnace. And the choice of the ores were very important. Some of the first experiments I was doing with iron ore from Corby wasn't rich enough and there's too much calcium in it. So we did a lot of work with pyroxene type slags sort of unnecessarily. Then we switched to other iron ore from Bekermet up in the Lake District. And on mass balances we came out with much better slag compositions in terms of what we wanted. And on the balance, in practical terms, we found that about 3 kilograms of iron ore flux plus 1 kilogram of copper ore was the composition of input materials to make the slag compositions that were comparable to the Egyptian compositions. Okay? And on a mass balance, we found that it was about 4 kilos of charcoal to sort of every 4 kilos of ore going through. But the materials didn't move through the furnace at the same rate. Okay? So based on these experiments, we could come up with a flow chart like this. It would be nice to sort of add some depictions with bellows and furnaces and ancient Egyptians in here and put it in a mortuary temple. But this shows basically the same extension to the production of copper for use in all of these other activities. So here's the smelting up at the top. In terms of important inputs, we've got high-grade copper ore, we've got iron ore, we've got the air blast, we've also got the charcoal ash that we have to accommodate, and we also have poor quality furnace linings. Okay? That material, all added and smelting, produced an intermediate black copper, iron-rich ingot that we had to refine, and then refining, we produced more slag and a Plano convex ingot. Okay? So let's look at this sort of question of Plano convex ingots quickly before we move on. With crucibles like this, it's very easy to make a Plano convex shape in there. Okay? The bottom of the furnaces, though, that we were finding, are a completely different shape. This is one of the ingots from the bottom of one of the experiments. I think 25. I did some 30 before I was stopped, before the money ran out. Okay, and this conforms to the bottom shape of the furnace. It's all copper. Okay, there's a little bit of slag still on here, but this is the remaining metal, and then the liquid slag flowed out, and this was very easy just to recover from the bottom of the furnace. like this. And this just lifted off from the burnt clay underneath. Okay? Now, I mentioned flame color. Well, flame color is very important because it relates then to the amount of air going through the furnace, the combustion rate, and also the way we measure it, the ratio of carbon monoxide to carbon dioxide. And this was measured and identified in the experiments as well, too, and monitored all through the procedure. We found different types of bellows, produced, of course, different characteristics. We used pot bellows, bag bellows, and concertina bellows. And on observations, this type of bellow here, the pot bellow, was actually far superior than the bag bellows, which would represent maybe an earlier period. So this is right out of the tomb of Rekmi-Ray. What are some of the benefits of these pot bellows like this? Well, the first one is that the airflow we can generate from that was much higher. Working at a good pace, stepping from one bag to the next, we could generate about 350 liters of air per minute. Okay, that's quite good. Also, it's very interesting that when one would shift weight from one bellow to the next, you get much further penetration of air into the furnace. So that also helps solve some of the problems that we had encountered with the fire brick. Okay? The concertina bellows, well, those are just as effective, but they're anachronistic for the time, and you can make this type of bellow to whatever size you want. Okay? But it's the pot bellows, that's the important aspect, because that allowed the dimensions on the furnace, the volumes of the slag, and all these materials to be processed. In terms of CO2 and the color, again, that was all monitored. And looking at some of the thermodynamics behind it, we can see that conditions in the furnace were not only enough to reduce the copper, but also enough to reduce iron. So iron's one of those aspects that I want to look at now in the furnace, because the iron and the reactions in the furnace all tie together to characterizing what was happening at this period for the furnaces. I've published this as well, too. This is looking at aspects of high temperature effects on furnace refractories, okay? And trying to estimate how much additional flux we would need to compensate for this and still produce the same compositions as slag. So again, on balance, and this is the type of product that we produce from the furnace. Here's this ingot that I showed you and the slag. There was some copper that ran out with this as well, too, but we don't find these structures. So the copper was probably about 2 kilos per furnace. All right. So there are many more details, and we really worked on this and used it over the years then. What parameters were readily monitored and controlled? Well, the rate of fuel consumption. Okay. From the tomb of Rekmi-Ray, we see that that was probably counted in terms of bags of charcoal that were consumed. Okay. Color of the flames at the top of the furnace. Well, just watching in terms of it wouldn't work if the flames were yellow. It would work with the flames blue. Okay. Charge qualities. Well, based on some of the experiments, it's been possible for one of our other students, Dan Levine, to go back and look at the Harris Papyrus and other sources. And he's come up with some further translations, improvements, refinements on the translations for different grades of copper ore and also intermediate products. Okay? So these quantities and quality of copper and iron ore, that all ties together in terms of something they would assess. Grades of MEFCAT, high-grade copper ore, a medium, and a low. We think we've got 3 in the texts as well. Okay? The bellows, operation of the bellows. Well, the bellows and the rate of pumping and resistance into the furnace, that relates to fuel consumption. That relates to what temperatures are achieved in the furnace. Okay? You can sense that very readily when you step on one of the bellows and there's some blockage in the furnace. You feel that as pressure against your step. So you try harder to push it out, or you do different things with different true layers to try and control that. So that's some of those observational controls taking place. And probably most important here, the quality and quantity of the recovered metal. Of course, that would be one of those parameters that would be closely monitored, probably at several different levels. How is the quality assessed? Well, working properties. and maybe color of the metal as well too. Let's look at that. From the smelting experiments, then taking the black copper like this, and again we can identify that in the text. If we take that and remelt it in the crucible, we'll get an ingot, a Plano convex ingot like this. This is one that I made earlier. And cutting straight through the middle, you can see, okay, we kept a very blue flame on the furnace. You can see iron, metallic iron, in the top of the section. Okay? So we've got copper with iron in it, now in a Plano convex shape. What can we do with that? Well, we can remelt it. This is just a little crucible hearth I made. And then for remelting, you can see the crucible slag on the top here. And of course, all these things were analyzed and monitored and weighed. And we could find that on remelting the copper under partially oxidizing conditions with not such a blue flame as before, because it's harder in a shallow hearth to get such reducing conditions, we found that the slag that developed on the surface in remelting was very iron rich, and that was coming from the iron in the crucible like this, reacting with oxygen and other fuel ash. So that was the crucible slag. So every time I found I remelted the copper, it improved in quality. Now, Pliny noted this as well too, but that's anachronistic. That's way too late. Okay? With refining and remelting, we found I kept getting better and better quality, and I started casting little bar ingots like this. And we let the students practice cutting on here and making metallographic sections and things like that. So we can track all those stages as well too to produce good quality copper. Well, what can we learn about this, and where does this sort of integrate, and where does this take the research? Okay. Well, let's start looking at this question of iron and the copper. It's been suggested, and you can maybe see it a little better on here. See the gray, the white metal up at the top? Okay. That's the metallic iron that's a byproduct then from copper smelting. And also the amount of iron in ancient objects, we can infer some quality with that as well too. Iron is recognized as a common constituent of many ancient copper alloys. Paul Craddock and Nigel Meeks in the British Museum in Archaeometry published a lot of this using some of the results from my experiments as well too. We've looked at this a little bit further, and again this is where some of the science comes in very handy, because this is what we call a phase diagram, and this helps us describe exactly what we're looking at right here. Okay. This is showing along the bottom the amount of iron with copper. And this is showing, the way this is presented, showing what we just were viewing, that some of the iron has a little bit of copper and some of the copper has a little bit of iron in it. But we have two phases and they don't really mix together. So that's really just what we're looking at. So we expect to find a little bit of iron in the copper, or a little bit of copper in the iron as a byproduct from this technique. Well, anyway, with the refining experiments, this has been picked up by Ernst Panichka, and he's done some other further work lining these up as histograms and looking at changes in compositions based on remelting and smelting and refining. Okay? So we can track a lot of elements in here and how they change with the processing. Well, this is very important, of course, because this gives us a key to interpreting all of these thousands, hundreds of thousands of analyses that have been done of ancient metal objects. Okay? Helps put it in perspective. And what elements we find partitioning out with the iron or the copper? Well, those elements in my experiments that didn't really change over here, of course, the gold, silver, bismuth, iridium, nickel, those are some of the main ones. Those elements that react with the technology over here, of course, the iron, the calcium, it goes through, there are a lot of them here. And then there's this group in the middle that are affected both by the quality of the ore and the processing as well, too. So that gives you an idea how complicated all this gets and what we're trying to do in terms of tracking effective changes with the technology so we can better understand ancient metal objects. And of course, we have to look at some of the chemistry as well, too, and what the properties of the different elements are as they react under oxidizing conditions or smelting conditions as well, too. So that's enough, I think, on the smelting. Let's go on to another type of ingot. You've seen these oxide-shaped ingots. No complete ingots have been found in Egypt, to my best of my understanding, but I understand some fragments have been found as well. These are from the tomb of Re. You see it being carried in on his shoulder here. Again, by weight, those are about 30 kilos. From the British Museum, Metropolitan, other places, they've got examples as well, too. We've analyzed hundreds of them from Sardinia that we've published, looking at different compositions of ingots and these big oxide ingots as well, too. And, of course, I couldn't not make one. Okay? So using the same type of furnace that we did for the smelting, it was very easy just recharging copper, 30 kilos, melting it with charcoal, and then casting it into a sand mold. And that's how we made the first of this series of ingots like this. This one's broken up and recycled several times. And looking at the metallography, some of the background information about this type of ingot, we found that because of the way the copper was melted, it picked up a lot of oxygen, and you can see this in the structure here, but the iron concentration was also decreased. Okay? So again, looking at those processing parameters, that affected the compositions. Okay? Now, were such large objects as those oxide ingots made in Egypt? Well, this is a real good question. Probably not. Why? Because the quantities of metals produced weren't as high as some other areas, like Cyprus, and plus all the lead isotope analyses of this type of ingots is really pointing to Cyprus as their original source. If we look at the mortuary temple here of Re, they're casting quite a large door right here. Okay? And if you consider these small types of crucibles like this from the tomb of Re, again, and further work from Kantir and some of the metallurgical evidence there for types of crucibles, the only way they could cast sort of 30 kilos would be using multiple crucibles like this, because each one of these little crucibles only holds about 2 kilos. So here, I think what they're trying to show in this depiction is that there are many furnaces like this that are found in rows, and then the process is taking more and more copper and casting it into this mold for the doors. So the ingots are used, these oxide ingots are used in Egypt. They're broken up and then remelted in crucibles. So it's, I think, a difference in terms of what activities we're seeing. High tech in terms of the copper production, but not such high quantities. They're still importing a lot of copper from the Mediterranean. We can trace that as well, too. And those are the types of materials that we see being broken up and used for production of objects, like the doors, but not making more objects. This is the ingot here then, and then on one of our experimental archaeology weekends from the Institute of Archaeology, we started breaking it up with a big sledgehammer. Okay? So it was very interesting the way that all sort of developed. Went on from there. Okay, so this question of the iron and the copper, this is very good because this leads into our interpretation now of iron objects from archaeological sites. Right. So we've published this in Historical Metallurgy and other places. Originally it had been proposed that the iron produced from experiments like these was separated and then used. Okay? Well, there are problems in terms of processing because we see on remelting, it's very oxidizing. The iron's lost as crucible slag. Could they actually recover metallic iron from smelted copper? Well, we wanted to look at this in more detail. And of course, the way to proceed on this is to study more artifacts. These are some very small iron pins and rings from the Egyptian mining temple at Timna. Okay? First analyses of these, surface analyses, indicated that there was copper with the iron. And that was the background for their interpretation as being a byproduct from copper smelting. On the other hand, when I started looking at these objects and doing sections of them, I could show then that in the metal remaining in the centers of these, there was no copper in that iron. So where was the copper? Well, the copper was distributed in the corrosion products around the outside. So surface analysis gave the wrong conclusion. Surface analysis picked up copper on the surface of the iron objects, hence the conclusion they were byproducts. But based on further microprobe work, there's no copper in the iron, and the copper that's present here, it's an effect of the burial environment. Copper is more soluble in burial environment, and it is plated out and it's attracted and deposited on iron. So that's the explanation for the copper on the iron here. Okay? So in practical terms, it would be very unlikely the parameters for recovery, iron from copper in its metallic state, it would be very improbable that the iron would be recovered in its metallic form. Okay? Iron would be contaminated with copper if it were as well. Okay, so let's look at a few other objects. Just to double check, I did another experiment on the iron and the copper from my experiments, and I thought, well, wouldn't it be interesting? Let's just try and melt out the copper. Okay? I can't melt iron with charcoal very easily, but I can melt copper. So I put it under some charcoal in a crucible, and I tried to melt the iron out. I made steel. I didn't melt out the copper. Oh, but this is actually quite remarkable because there are all sorts of implications in terms of trying to deal with mixtures of copper and iron. So anyway, that's some of the experimental background. If we start looking now at iron objects in context, well, what technical features characterize early iron? Well, some of the earliest iron objects are from pre-dynastic tombs in Egypt. We've got some in the Petrie Museum. Other people have studied them, Desch and others. We managed to get hold of a few little fragments, and we've checked these. And what's very interesting about these pre-dynastic beads, they're totally anachronistic, but of course they've got nickel in them. Okay? And nickel over about 5% is usually used as an item, technical feature that characterizes, of course, meteoritic iron. Okay? So those don't have anything to do with this story I'm trying to tell you. Okay? That's an important threshold, though, because if we look at the iron dagger in the tomb of Tutankhamun, okay, back in about 94, but presented in 95 at a conference we tried to organize, and well, it's easy to start something. It's harder to keep it going, as you all know. Fatma Helmi and Kamal Barakat did surface analysis of the iron dagger, and they found there's about just under 3% nickel. Well, their interpretation of that was that since the nickel concentration is so much lower than known meteorites, their interpretation was that this dagger was not made from meteoritic iron. Okay, well, that's really interesting. And when you consider these other miniature iron tools, also from the tomb of Tutankhamun, those are very interesting, and I think those should well be checked as well, too. Here's a few other objects. These are some iron bracelets from the Bekaa Valley in Jordan. They've been studied by a group at University of Pennsylvania. And it's very interesting that these late Bronze Age iron bracelets in metallographic section and composition, they're steel. Now, why would anyone make a steel bracelet? Well, maybe not understanding the processing and how easily iron accepts carbon to change structures. Okay? And these have been analyzed, and one of the things to note here, okay, that the copper, where's copper? Here's copper. Look at these copper concentrations. They're all very, very low as well, too. So again, this is indicating, okay, they're not meteoritic. They're not byproducts from iron smelting. So these are deliberately produced bracelets. Okay, well, this is all sort of moving along. Let's go back to Egypt again. Going through Lucas and other sources, trying to track down, well, what are the earliest textual references to iron and steel? Well, we've got from the Amarna texts, lists, laundry lists of royal gifts, probably of Hittite origin. And these were types of objects that are recorded as having been given to Amenhotep III. Okay, so a dagger whose blade is steel, another dagger. You have to be careful with the translations here. You always have to assess that in terms of what steel, okay, and assessing that. But anyway, iron. Certainly they're getting iron right? So these are iron daggers and iron rings, some with gold. All right. So next is, have any of these objects, for example, listed in Amarna letters ever been identified? Well, wouldn't that be nice? One of my PhD students now is working in central Turkey at the site of Kamen Kalyuhuyuk. She's doing her PhD on early Hittite iron. We're getting a much better idea now what the Hittites were capable of doing. We've seen what the Egyptians were doing, those little tiny pieces of iron. But this is an example of a Hittite knife excavated from the site. And over here on the left, these are some examples of some iron knives that Tolander worked on from Cyprus that are late Bronze Age, a little bit later. But in terms of typology, some of these well-dated knives here from Cyprus were always kind of, they seem kind of odd, almost sort of too advanced. Okay? But here we've got one that's excavated that's stratum 3, so it's Hittite date, very unusual shape on there. And I did bring along a poster that my PhD student did for another conference last year on the world of iron. Okay, so I brought that along if you want to see some of these other objects. But more and more are being published. They've got a metallurgist working on it, Akanuma, and they're doing more and more on Hittite iron and the properties and characteristics of Hittite iron. Okay? And there's really quite a bit of it. Now, this isn't a royal site for Hittite, so it's not the highest quality iron, but it's very, very good quality iron and steel based on the metallurgical studies. So if we go back to Egypt again here, what's sort of the next step where they're producing maybe comparable material? Well, based on analyses by Alan Williams and Rachel Maxwell Hislop on some of the Assyrian period iron objects, these are showing some of the characteristics that we're also seeing for very early iron objects. So again, this is one of those technologies that seems to be coming later into Egypt. So high tech for the copper, low tech so far for the iron, not on quantities. So one of the projects we're thinking about doing is further analysis of some of the Petrie objects, and again trying to highlight whether we can identify on technical parameters some of these other objects. And we're getting more information about types and the technology for Hittites. So to sum up here and finish, evaluating experiments. How similar, how different are they to the archaeological remains? Again, to emphasize a point before, with the technical studies and analytical data, we can be more confident on aspects of some of our interpretations. Okay? So in terms of looking at the evidence and the aspects, we can start beginning to assess, now as more and more analytical work's being done, just how sophisticated something is, how functional, how good, how technologically advanced. And of course, we're discussing these in modern terms and going back to assess ancient materials. We still have to think about those in context. So again, with the experiments, we use these to reformulate questions, maybe help direct research, target specific types of objects, and from there trying to build further in terms of our prehistory or history or philosophy or prehistory or philosophy of technology. There are all sorts of aspects that could categorize it, but looking towards better interpretations of metallurgical remains, better understanding of technological skill, and assessing past capabilities, recognizing uneven achievements and appreciating diversity. And finally, New Kingdom Egyptians appreciate gifts of steel. Okay? I think that's where we'll finish. Thank you.
Thank you very much, John. That was very interesting. Have we got any questions? We have got time for a couple of questions. Alan?
I'm greatly intrigued by the representation in the tomb of Regmire of casting the door. It's puzzled me for a very long time. I was there in March, had another look, and still came away puzzled. I assume that, in fact, the mould wasn't filled in that vertical position. I assume that that's the Egyptians simply making sure we know what's going on, and that the thing was in fact laid horizontally. But the thing that really troubles me, and this shows my ignorance of metallurgy, is the question of whether, with all these funnels feeding bronze into the mould, the question of whether there'd be a problem of differential cooling, and if such a problem is a potential problem, what could they have done?
Okay. Number one of the real unusual aspects of that depiction is the size of the door. Yeah. What are they actually casting in there? It's not a thin layer, so it must have some relief to it. And I can't imagine, are there any examples of a door that might be that size extant? Yeah, but something like that, of course, would be broken down and recycled eventually. But no, I think it probably was cast vertically, and there's so many risers on there, and runners as well, too. I think they're showing both, that it looks like it would probably be cast from crucibles all at the same time, okay? Vertically, like that, would allow better escape of some of the gases and things as well, too. And I don't think they're casting very thick in there. It could be a centimeter or so, maybe on each surface, or maybe just part of the surface. We don't know what was inside the mold.
You couldn't presumably have a situation where somebody says, right, we all go now, get pouring. Surely it would have to be done in a relay system, and the bronze door would actually be stratified.
Yeah, that's the way that large castings are usually done. But the mold does retain enough heat that you don't get separations between the different pores. So, for example, one of my past student, that's the sculptor and the founder on here, he does multiple pours. He has several crucibles all lined up and ready to go, but he pours each one of them. But the mass of metal is enough that it doesn't chill that quickly in the mold, so the second one comes on top. On the other hand, if you wait too long and some solidification begins really to start in there, and the second mass of metal doesn't remelt some of those surfaces, then you can get some layers. And some of those layers have been identified on late Bronze Age oxide-shaped ingots. So it looks like there may be multiple pores to make it. But again, it comes down to timing. It comes down to timing and the quantity of metal. And those are some of those aspects that we don't have a handle on for this size of an Egyptian casting of a door, which is absolutely remarkable. Yeah.
Thank you, everybody, and thank you especially to John. There's obviously a lot more to talk about.